Swayam Prabha. Digital India. Educated India.
So, okay, in the last class we discussed that static stability analysis is not really enough to comment on the stability of aircraft in motion, right, and thereby we have to look at the dynamic response, okay, of the perturbed variables from a particular flying condition, right. So, let have to look at the time response. So, to look at that, you need to first write down the equations of motion of aircraft, right. So, remember that we while doing static stability analysis, we have not really taken care of the mass, inertia and damping properties of the aircraft, right. So, all those will come into the equations of motion. Right. How many equations? How many degrees of freedom an aircraft will have? Aircraft is an elastic body, right. So, if you include all the elastic modes and elastic vibrations, then there will be some infinite degrees of freedom, right. But do you think it will be important everywhere? For big aircraft with large wingspan, right, where the wing can actually display some motion, isn't it itself, no, because of the aerodynamic loads, there it may become important to include those effects, right. But for our purposes, we will stick to a rigid body motion of aircraft, okay. So, we will assume the aircraft to be a rigid body, right. So, first assumption that I am making here is that aircraft is a rigid body, right, and a rigid body can have how many degrees of freedom? 6 degrees of freedom, right. Okay. So, 3 translational degrees of freedom, right, and 3 rotational. Okay. So, what else you have to define before you start writing equations of motion? You can use Newton's law, right, and Newton's law requires that you should have a inertial frame of reference, right. So, we will assume earth to be a non rotating inertial frame of reference. So, I am writing non-rotational specifically because we do not want to include the effect of rotation of earth on the aircraft dynamics, okay. That will be negligible because we are working at lower heights, right. And for our engineering purposes, this will be sort of a valid assumption. Once we have these two assumptions written down, I think we can start writing our equations of motion, right. Let us say this coordinate system is fixed to a point on earth, right, and this is our aircraft which has mass m. So, this assumption automatically means that there is no relative motion between any 2 points on the aircraft, right. Let us call this point C as the center of mass of the aircraft. Right. So, what we will do first is we will write force balance or momentum balance equation for an elemental mass and then integrate it, right, all over the aircraft. So, we will look at this elemental mass delta m, right, and this delta m is at a distance small r from the center of mass, right. Distance between the center of mass of aircraft and the origin of earth fixed axis system is RC, okay, and this bar indicates it's a vector, right. We have to talk about x, y, z coordinates, isn't it? Okay. Let us say this is R, right. So, we can use the vector notation and write what this R is. R is isn't it? Okay. And let us say this center of mass of the aircraft is having a velocity v c. So, this could be all right. So, and we will also assume that the aircraft is rotating, okay. So, it has an angular velocity which is denoted by this. I can write a subscript be attached to this, so that is the rotation of the aircraft in the body fixed axis system, okay, isn't it? So, it has three components P, Q, R, we know that, right, roll rate, pitch rate, yaw rate. So, what would be the velocity of this elemental mass? If I say that aircraft is a rigid body, then this mass is not going away or coming closer to the center of mass, isn't it? So, what other velocity it has? Angular velocity, right. So, this omega b into this distance r is going to give a tangential velocity, and the center of mass is having this velocity v c, right. So, we can write the velocity of this elemental mass, which is plus omega into r, right, omega cross r, very good. Okay, let me put this bar also on top. Right. Sum of all the forces acting on this elemental mass, right, is what is going to set this in motion, right. That is how we balance out the force. So, if this is the force acting on the elemental mass delta m, then the equation of motion can be written in the simple form using Newton's law, right, F equal to m into a, right, and acceleration is the rate of change of velocity, right, or time rate of change of linear momentum is going to give you the force. Now, use this expression for V and you can further expand this. This omega b is actually independent of this elemental mass, right, is the fixed angular velocity vector, it does not depend upon the mass. So, you can also write in the further step this equal to this, right. If you sum this up, then what you get is the total mass of the aircraft. What about this quantity? This is, yeah, okay, time rate of change of this is missing, right. Let me just, okay, you are right. So, we will have to rewrite this. Yeah,
dr by dt is 0.
dr by dt is 0. So, you can also look at another representation. Okay, but right now it's all right. What you said is correct. No, but we can also write it in a different form and see what that gives you. Right? Okay. What this quantity is? So, one thing is that dr over dt is 0 because you are saying that the aircraft is a rigid body. So, there is no relative motion between the 2 points, right, and so that is also correct. Second representation is this, right, and what is this quantity? This is 0, right, because we are measuring all the distances from the center of mass of the aircraft. Is that clear? Right, because I am measuring all the distances, the small r, from the center of mass. So, this summation is 0, but this is the definition of the center of mass, right. Any question? Okay. In mechanics, you have also studied that if the body is a rotating body, okay, then we will also have to incorporate other accelerations, right. So, our aircraft is actually rotating, no, it is having some angular velocity. So, this term will have two components, isn't it? You know that if you have any vector A, rate of change of that vector as seen from the inertial frame, right, is going to be equal to rate of change of that vector as seen in the body, right, plus into all right. Okay. So, this you must have seen this somewhere, okay, and we are going to use this, right, because it is not important for me to explain you this in this course. So, I will just use this and write down the force balance equation right. What is my Vc? Vc is the velocity of the center of mass of the aircraft, right. It will have 3 components, right, along aircraft fixed axis. Right. So, aircraft is having velocity component along its axis, u, v and w, right. So, now I am ready to expand this. Okay. So, let us see what we get after expanding this. I, j and k are unit vectors along aircraft body fixed axis. So, now I can find out the equation of motion along x, y, z axis of the aircraft. And this force is going to be sum of all the forces acting along the axis of axis of the aircraft, right. This is what is going to give you this. So, I will put a subscript B here to indicate that these forces are along aircraft fixed axis. Right. So, we have 3 force equations. And now, what else I need to write? We have to write 3 equations for the rotational motion, right. I will assume that there is a external moment acting on this elemental mass delta m, right. So, the moment is right, external sum of all external moments acting on the elemental mass m, and this is going to be equal to how do you write moment? Like force is the rate of change of linear momentum, right. So, moment is rate of change of angular momentum, right. Let us say delta h is the angular momentum of this elemental mass delta m. Okay. So, m is this. What is delta h? R cross V, V is the velocity of this elemental mass delta m into delta m, right. That is how we write the angular momentum. Right. So, R is depending upon this mass m. So, I am clubbing these two together, and Vc is actually independent, right. This velocity of the center of mass. So, we can keep it separate. Now, as long as you are following this much is all right for this course. Okay. For any detailed explanation on this or mathematical description, you can go back to your classical mechanics course. Would have done a course in mechanics, right. So, this becomes 0 again for the same region that we are measuring all the distances from the center of mass of the aircraft. So, this term goes to the 0, and let us expand this. Okay, we will try to expand this. So, we will assume the coordinate of this elemental mass delta m to be x, y, z. So, R is okay, and I, j, k are unit vectors Let us see what we get when we expand this. Is this correct? No problem here, right? Right. So, I have found an expression for the components of this vector h along body fixed axis, right. So, what is the x component? This into delta m, and we have to sum it over the whole aircraft. Yeah. Then see any mistake anywhere?
The second row of the matrix. So on the first above you have given r as x comma y comma z. Here r to the minus p to
Okay. So this yeah. Thanks. You should keep doing this, okay? When I am making mistakes, you should tell me. Otherwise, we'll have to. Right. Okay, so now I am ready to write the x component of this vector. along body fixed x axis. Is this all right? So, you have components of angular momentum vector along the body fixed x, y and z axis, right. So, if you want written this B for body, aircraft body. I think we'll stop at this point.